SAT Modulo Symmetries for Graph Generation by Markus Kirchweger and Stefan Szeider. Many problems in combinatorics can be phrased like this. Does a graph on n vertices exist with a certain property x? A common approach to solve this question is to use a tool like Naughty to generate all graphs modulo isomorphism and then check for property x. So it's a generate and test approach. Why do we want to consider only graphs modulo isomorphism? Yeah, the search space is enormous. So this is the search space without considering isomorphism. With isomorphism, it still explodes, but it explodes slower, so to speak. But already with 11 vertices, we get more than 1 billion of graphs modulo isomorphism. So here are, for instance, 2 graphs that are isomorphic. Now, how can we check for isomorphism? We can look at the adjacency matrix of 2 graphs that are isomorphic and only consider the one where the adjacency matrix is smaller in the lexicographic ordering. And we will always only consider the smallest graph with respect to this ordering. We will only have one graph from an entire isomorphism class. So a static CP approach would proceed like this. We combine now the generation and the test in one process. We take the conjunction of 2 constraints. One constraint represents the graph property. Let's call it graph x. And in this encoding, we have a Boolean variable where for each pair of vertices I and j, we have a variable that's true whether or not this edge is present or not. And we can now take this encoding, feed it to a SAT or CP solver, and it will then only generate graphs modulo isomorphism. However, this approach has one problem. To encode this lexicographic minimality check in a complete check, then it requires an encoding size that's exponential. Hence, the idea is to relax this minimality check and only check that we can't permute k vertices to obtain a lexicographic smaller graph, where k is usually take a small constant, for instance 2. This works, but the filtering, so to speak, is not very good. We still generate a lot of copies, isomorphic copies of the same graph. Now our approach is that we call SMS, SAT Modulo Symmetries, to still get a complete minimality check in the solving process. So the idea is to use an external test for lexicographic minimality within a CP or SAT-based graph search. And this check integrates perfectly in a CDCL SAT solving framework. And here, even a complete minimality check is possible. So the idea is that we only encode this graph property with clauses or constraints, feed it to a SAT solver, and the SAT solver then calls frequently an external propagator, a complete minimality check. And when this graph that might only be partially defined at this stage is sent to the minimality check, the minimality check tests whether this partially defined graph can be extended to a minimal graph or not. If it can't be extended, then a clause is learned and this clause is sent back to the solver. Now, I mentioned partially defined graphs. This is a new notion of our paper. This is a graph where now, for some edges, it's undefined whether this edge is there or not. So we can draw such a graph by using dotted edges to indicate undefined edges. And we can also look at adjacency matrix where now an undefined edge is represented by a star. Let's again look at this partially defined graph G. This is now a set of 8 possible extensions of this graph to a fully defined graph. Now, there are 3 undefined edges, and so we have 2 to the 3 is 8 possibilities of extending this graph. And we consider the partially defined graph to be minimal if at least one of these 8 graphs, or in general one of these graphs to which it can be extended to, is a lexicographically minimal graph. And now in our SMS procedure, it learns a clause in Bedrex if it arrives at the partially defined graph that isn't lexicographic minimal. Here is an example for our minimality check. Here again to the left is this partially defined graph and the corresponding adjacency matrix. And now we do a branching algorithm. We start by trying out which vertex in this permutation comes at place 1, and then in the next level which vertex comes at place 2, etc. Let's look at this branch here where we say the vertex 3 comes first. Now we draw the adjacency matrix accordingly. If the vertex 3 comes first, then, and we look now at the row of vertex 3, we now see that the vertices 3, 4, and 5 have not an edge, there's a 0. So in a lexicographically minimal ordering, 3, 4, and 5 need to come first. 1 and 2 come later. And already here we detect a contradiction because this column, the third column, would now get a 0. However, in our original graph, we have here a 1. So we already found a permutation that gives us a lexicographically smaller graph. And actually, for all possible graphs that we can extend these partially defined graphs to, we will always get a lexicographically smaller one. Therefore, we can extract a clause that forbids this particular configuration and send it to the SAT solver. Of course, in this case, we were lucky. Already in the first row, we found the contradiction. But if the first row works out, then we go in the branching algorithm to the second row, to the third row, and so forth. This minimality check is in the worst case exponential. So when we really need to go to the last row, in practice, we don't observe this exponential runtime behavior. And in some cases, this minimality check finds an implied edge. So it finds somewhere a star where, under the assumption that the current graph is lexicographically minimal, it knows that this star must be a 0 or the stars must be a 1. So it not only rejects a partial graph, but it can also learn that there is an implied edge or an implied non-edge. We implemented the SMS framework using Klingo as a SAT solver, and we have this min check, this propagator implemented in C. We also have here the parameter frequency. So we don't call minimality check each single time when a new edge decided, but only, let's say, every 5th time an edge is decided. Because the minimality check can still be quite costly, and overall it suffices to check only all couple of times. And we also implemented the static symmetry breaking that checks of whether swapping two vertices makes the graph smaller. And so we could compare both approaches, the static and the dynamic one, within the same framework and the same solver. And now we tested this implementation on 2 showcase problems from extremal graph theory. One is related to the girth of the graph, and the other one is related to the diameter. So the girth is the length of the shortest cycle, and the diameter is the longest distance between any two vertices. And now for girth, the question people from combinatorics have asked was, what is the largest number of edges a graph of girth greater than k and n vertices can have? And we can denote this number by f index k of n. So we want to compute this function. And there is actually a theorem by Int'l that's more than 100 years old, which settles the case for k equals 3. However, for k is 4, 5, and so on, no closed formulas are known. And now we propose a Cna formula, f, that depends on n, m, and k, so the number of vertices, the number of edges, and this girth lower bound, which is satisfiable if and only if there exists a graph of girth k with n vertices and m edges. And now we can check the satisfiability of these formulas with gradually increasing the value of m until the formula turns unsatisfiable. And with a lemma by Garnick et al., we can get some lower and upper bounds on degrees of the graphs, which helps us to a little bit bound the search space. Here are some results for k equals 4. So we see results for the satisfiable case and the unsatisfiable case to the right. And we have the SMS, one column for the SMS approach and one column for the static approach. Here we see the results for n. All these running times are in seconds. And in parentheses for SMS, we always give the percentage of the total running time we have spent for the minimality check. NA means that the upper bound is covered by the Bench's lemma, so we don't need to compute it. And we have a timeout of 4 hours. And DO means this timeout has been reached. So here we see that the SMS approach is often quite significantly faster than the static approach. Sometimes we also get a solution where the static approach reaches a timeout. And we also see here that the percentage spent on the minimality check is most of the time bigger than 50%, both in the satisfiable and in the unsatisfiable case. Here we tried also to see what impact the frequency parameter makes. Here we have one satisfiable and one unsatisfiable instance, just to give you an idea. It turns out that for the satisfiable instances, the frequency parameter is quite crucial, but to use the right one. So here we see that something between frequencies 1/5 or 1/10 has the best running time, whereas for the unsatisfiable case, the frequency doesn't seem to have such a strong impact. Here are the results for larger girth. Here we implemented the girth condition differently with more auxiliary variables, which means that the solving part is more complicated and therefore the minimality check part is more dominated by the solving part. Therefore, we see in the parentheses the percentage of the minimality check quite smaller than we have seen for k equals 4. Now to the second showcase problem, diameter 2 critical graphs. So a graph is diameter d critical if its diameter is d, but by deleting any edge, the diameter decreases. And the question people from combinatorics were asking for decades now, how many diameter 2 critical graphs with n vertices and m edges exist, modulo isomorphism. And again, we can denote this number by d2 of n and m. The Simon-Murty conjecture from 1979 says that for a particular number of edges, which actually corresponds to the graph being a complete bipartite graph, then there exists only one solution, namely this complete bipartite graph, and for more edges there are no solutions at all. Again, we have a SAT encoding for this problem, and we use lemmas from combinatorics to obtain suitable degree bounds. Here are also the known results in green. People have used Naughty to compute the solutions up to n vertices and could therefore also verify the Simon-Murty conjecture for up to 10 vertices. With our SMS approach, we could now also enumerate all solutions up to 12 vertices, and just verifying the Simon-Murty conjecture, we don't need to count all the solutions, but just verify that this solution is unique. We could go up to 18 vertices. We introduced the SMS framework for graph search. We could accomplish to do a full or complete minimality check with an external algorithm integrated into a CDCL SAT solver. Important ingredients is to check lexicographic minimality for partially defined graphs. And we evaluated our approach on showcase problems from extremal graph theory, first on girth critical graphs, and second on diameter 2 critical graphs, where we also could confirm the Simon-Murty conjecture for up to 18 vertices. For future work, of course, there are many, many more applications. We would like to try the SMS framework on. One can also adapt it quite easily to other combinatorial objects than graphs. And one thing we also want to work on is to further improve the minimality check to make it faster. An interesting thing for experimental evaluation is to have a dynamic setting for this frequency parameter, not just to set it for a whole run, but maybe dynamically change it up and down depending on how far we are in the solving process. Many thanks for your attention.